Uh, Anything else you want to talk about or ask that was there in the course?
Sir,
Yeah.
EM reverse bias, sir, can you explain?
Okay, sure. Your name is showing up as Vivo. So what's your name?
Sandeep Chatterjee, sir.
Sandeep, huh?
Summers in the sir.
Okay, fine, fine. So you want to understand how the reverse bias operation happens. Is that what you want to understand?
Yes, sir.
Okay. Let's think of a PN junction like this. So if you don't apply voltage, there's going to be some built-in field, correct? Now, what is the charge on this P side? Let's say this is P side, this is N side. What will be the charge on the P side, Sandeep?
Sir, positive.
Positive. P type, P side, P side.
Sir,
In PN
negative.
junction, negative charge, right? This side will be negative charge. Why is it negative charge? Why is it negative charge?
Due to sir P type.
Yeah, P type, but why should it be negative and not positive? P has lots of holes, right? This essentially means this has a lot of holes. Majority carriers are holes here, and here the majority carriers are electrons, right? So why do we get negative there on the P side? Should remember that this is basically what we call a space charge, okay? These are what we call as space charge regions, okay? These are consisting of immobile, donor, or acceptor ions, okay? So what happens is your holes move out. So holes are positively charged. When they move out of this region, what is left behind is negative charge. So it's an ionized acceptor in this case. On the N side, we have ionized donors. Is that okay so far? Right?
Yes, sir. Yes, sir.
So now, if you apply reverse bias voltage, what happens first of all? Okay. So when you apply reverse bias, let's consider this scenario wherein I apply a negative bias here, then I connect this fashion, external circuit. So what should happen is your holes are the majority carriers. They end up coming from the edge of the depletion region into the terminal. Here the electrons will come out, and what you end up having is basically a device with a larger depletion width. Okay, so you have a device now like this, wherein let's say the depletion region has become wider. Okay, negative charge on this side and positive charge on this side. Why is it wider now compared to the uncharged case? As you increase the negative reverse bias, as V reverse increases, the width of the depletion region increases. W, right? Increases. Is it clear why this should be? Because think of it like a negative, positive terminal here. So it's going to pull in some electrons into the circuit outside here. So where will the electrons come from? Will they come from this edge here? No, because this is all a conductor, right? So essentially the electrons have to come from the edge of the depletion region. So these electrons are moving out. When they move out, they leave an additional amount of charge at the edge of the depletion region like this. And similarly, another edge of charge, right? So the overall charge has increased.
Yes, sir.
So now, if I have to ask you one simple question, can you draw how the charge profile looks like in these two cases? Let's say this is voltage V1. Okay, this is V1, and this is voltage V2. How does the charge profile look like as a function of X? What I'm asking you to do is think of this X, and this is your, let's say, rho, some charge. How does the charge look like at V1? You have till 0, you have a negative charge on this side, and here you have a positive charge. Let's call this as XL, and this is minus XP. So this is XL, this is minus XP. This is how the charge profile looks like, isn't it?
Yes, sir.
Agreed? So now, if I apply voltage, how does the charge look like now? If I increase the voltage, if I say that V2
The
is greater
negative
than V1,
increases.
yes, how does the charge profile look like? I'll give you two options.
Yes.
Okay, I'll give you two options. One option is this: the negative charge and the positive charge are increasing, no? Correct? So essentially, you have a larger amount of charge here. Okay, and I'll give you another option where you have the charge profile to be this. Okay, so you have option
Second
one.
option, sir. Second option.
Why is it second option? Why this is option two and this is my option one? Why should it be the second option?
Due to the reverse bias and uh, elect, po- po- elect, positive ion.
Correct. In both cases, no, I can have a larger width or larger charge, right? I can have the same area, right? I'll make sure that the area of this rectangle is equal to the area of this rectangle. The total charge, I'll make sure it is same. So why should I prefer two and not one? TS, can you just please take a screenshot of what I'm drawing and just add it to our sheet, please? Okay. TS?
Yes, sir.
Yeah, please add this sheet, this screenshot, what I'm drawing into the sheet that we are discussing in the morning, the common sheet. We want to use it for questions we thought, right? That one. Yeah. So, is it okay? Ritu, Nandana, somebody can take this? Yeah. Tell me now, Jeet, or Sandeep, I think. Why is option two the correct answer and not option one? Hmm? Hello? The reason for that
Due to
is
the whole makes a law.
no. The important thing to realize is we are assuming a uniformly doped semiconductor, right? This has a doping density of ND, and this has a doping density of Na, right? So these are uniformly charged semiconductors. That means what is the extent of magnitude of this charge? This is Q times Nd, and this is Q times Na, the charge density, right? So this is the doping density, and here it is a doping density. Now, as you increase the voltage, you cannot change the doping density. You cannot change the concentration of donor ions, right? These are donor ions. Okay. As V2, when V2 is higher, when V2 is greater than V1, the concentration of donor or acceptor atoms cannot change, correct? Agreed? Got it? So the answer has to
Yes,
be
sir.
2. Answer is basically 2. The concentration remains same, the magnitude of the charge remains same, but the extent of this will change. Okay, this is the right answer. Got it?
Yes, sir.
You cannot keep the width fixed and then increase charge. This won't happen. This cannot happen. Okay. Now I'll ask you another question. So now, once you have the charge, right, you know how the electric field looks like, correct? Let's assume now, simplify this. I'll remove some, okay, I'll take this charge once again. I'll say that my charge looks like this and this, xn minus xp, plus and minus. Now, how will the field be when you have a diode like this? This is rho, space charge. How will the field be? Can the field be like this? First of all, these are uniformly doped semiconductors, right? So the field basically will, you can actually compute the equation. The governing equation is dE by dx equal to Q NA or ND by epsilon. Correct. This is the governing equation. So electric field is E is linear. With me so far? So now, can I have this as my equation, my electric field? I have P and the N regions. If I take I have a charge. Based on the charge, I should have a linear electric field. Will this be correct equation? Correct way of electric field? Well, the problem here is the electric field is positive. But you know that when you see this picture, the electric field is going from positive to negative charge in the negative x direction. So electric field has to be negative, not positive. Okay. So we say that now my electric field is going to be this. Okay. This is my xn. This is my xp. Correct? This is my electric field. This, let's say, is at V1. Okay. As I increase my field in the reverse bias, what happens to the electric field? How will the electric field look like? Again, I'll give you two options. I'll say one option is electric field looks like this. Okay. This is one option. Okay. Another option is I'll have electric field which looks like this. Okay. Now, which is the right answer? Got it? Let's say this is my option 2 and this is my option 1. Right? This is the E field at V1. Correct? These are my situations. Now, when you have such options, what will be my electric field? Yeah?
Yes, sir, but
1 and 2. My voltage has now increased to V2. Okay, what is E field at V2 greater than V1? I have more reverse bias, let's say. What happens? The depletion width should increase. So the depletion width has increased here and here, right? Both sides the depletion width has increased. So that is correct. And the amount of voltage drop across it also is higher if you take the potential drop. Huh?
Option 2, sir.
Option 2, why? In this case also the potential, right? The potential is increasing. Here also the potential is more in both options. But why is option 2 correct? Why not 1? Yep. Okay. Why? The answer to that question is, what determines the slope of this field? dE by dx is equal to how much?
పరిగెత్తాలా కానీ మనశ్శాంతితో పరిగెత్తాలా
Hello. So what is the electric field slope dependent on? It depends on Q times ND. Absolutely. Correct? So this doping density is fixed. Just because you are changing the bias, the doping density doesn't change. So the slope of the electric field should remain the same. So the peak has to change. Does it make sense? Your peak cannot be constant. In this case of option 1, the slope has changed. Just because you applied a voltage, the slope of the field cannot change. Okay?
Yes, sir. Yes.
So it has to be like this. So
Okay.
now, if you have such a scenario, and other side, of course, is, this is basically dE by dx is Q and A by epsilon, right? So now, when you have a situation like this, what will be the potential? Well, the potential is what is causing it. I mean, you can do it in different ways. So we know that dV by dx minus of dV by dx is equal to electric field, right? So basically, voltage or potential drop is going to be integral of dx. Okay, you compute the integral and you can see that. So, I mean, you can also see another way, that is, you can take some reference and you essentially say that there is a voltage drop. So this is, if I apply this much of potential on the edges, if this is my 0 volts, if I apply, there is an electric field which is going in the negative x direction. So this is my potential, okay? Now, when you have this kind of a potential, that means the positive charges will actually move away from the junction. So the positive charge, if it tries to cross this, it cannot cross it because the electric field is in the opposite direction, correct? So the holes will see this side is holes, right? P type. This is P type. So holes see a potential barrier. Okay. Similarly,
Yes, sir.
you have a lot of electrons on this side. The electrons will tend to move which direction? Opposite direction, right? The electric field is in this direction. Electrons will try to move in this direction, right? Electrons will move away from the junction. So again, they cannot
sir.
flow. So essentially what you have created is a barrier. Okay. Now, if I increase the reverse bias, how does the barrier look like? If I increase bias, reverse bias, I'll have a slightly, larger barrier like this. The potential barrier increases. This is, let's say, my V2, and this is my V1. So in the reverse bias, as you increase the reverse bias, the potential barrier increases, and you cannot have flow of current. All right? Agreed?
Right. Agree, sir.
But then the problem is you don't only have, we said that you're going to have, this is the direction of electric field, isn't it? This is my direction of electric field here. So here, majority carriers are electrons, but there are minority carriers, correct? The minority carriers, if I take this, is P, this is N. Here, minority carriers are basically, in this case, electrons. Okay, here the minority carriers are holes. Now, my field is in this direction. So the minority carriers can easily flow across the junction, right? But not the majority carriers. So even though you have reverse bias, you have some leakage current because of the minority carrier drift across the junction. All right, got it? So this is how essentially you have an IV characteristic of a PN junction, which looks like the standard, whatever we know of. So as you apply positive voltage, the depletion width reduces and you start seeing increase in current. In the reverse bias, because of the way the field is, the minority carriers can flow and you essentially have a current which is small reverse saturation current is what we call it. The number of minority carriers is quite small, so you can't have a large current in the reverse bias. Okay?
Got it,
Correct?
sir.
Yep.
Thank you, sir.
All right. Yeah.
Sir, my last question is that
Sure. Tell me.
for examination, how each chapter can I focus more?
See, I think we'll have we have roughly 4 or 5 questions from each week. Okay, in the examination, we'll have out of 4 or 5 questions in each week. 1 or 2 will be from recall. I mean, just by lectures you will have, and 1 or 2 will be from assignments. And there'll be one new question that you have probably not seen. I mean, there'll be something that based on what you have understood, but one new question. Okay. So if you do the assignments and you just broadly know what is happening in the lectures, you're fine for the examination. Okay. Every week we'll roughly have one question. May not be, week 11 and 12 may have slightly less weightage. There are in effect 50 questions. Okay, total. So 12 weeks. Oh, okay, yeah. 4 questions in each week, roughly, on average. All right.
Okay,
Does
sir.
it help? Yeah. So there's nothing like, what do I focus on? It's all kind of uniform. We just go by weeks and we just pick up 2-3 questions from each place. Okay, 3-4 on an average 4 questions per week. Only week 12, 11 and 12 will have slightly lesser weight. Maybe there are only 3 questions each or 2 questions each. I'm not certain. Okay. Yeah.
Okay, sir.
There
Thank
is
you, sir.
Thank you. Yeah. There is a chat from Sandeep. Sandeep, oh, that's very good. Okay, can somebody read this for me?
Yes, sir.
Yep.
Sir, he is asking what is the difference between photodiode and solar cell? First
The operation is very similar. There's no difference. Okay. Oh, well, I mean, photodiode, okay, there is one small difference. The photodiode, you typically reverse bias it so that you have a large, sorry, I'm sorry, 1 second. I'll just mute it. This is Monica calling. Can somebody call her and tell her that I'm in the lecture? You have the
Okay.
number? Yeah, please
Yes,
call
sir.
her and tell. So, yeah. So in a photodiode, we typically reverse bias it. And we also make sure that, the configurations depend on which detectors we use. But typically, they also have a large intrinsic region so that you maximize the absorption efficiency. Okay. And then there's a photocurrent that comes in. A solar, and in this case, we want to have maximum amount of current produced per photon. Okay, we want high quantum efficiency detectors. A solar cell, on the other hand, is like, it's not, similar reverse bias junction can work as a solar cell. But, sorry, in that case, you don't bias it actually. You just shine light and there is this potential that, rather the current that flows in an external circuit, and you put many of them in series and parallel so that you can drive household appliances. Okay, you don't bias a solar cell. You don't put a battery for operating a solar cell. It's just, because of sunlight, there's a certain amount of current that is produced because of the light induced generation, and that flows in an external circuit. All right. Whereas a photodiode, typically we would like to bias it so that it's much more efficient. The importance in a photodiode is actually what we call as responsivity, right? We want to get more electrons per photon. Okay. To get a higher responsivity, you essentially need to have, you typically bias this in reverse bias. Okay.
The second question is
Does that answer, Sandeep? Does it answer your question?
Yes, sir.
Okay.
I got it.
Yeah. So what is the second?
when light is incident on a PN junction based solar cell from one side, would not we have a diffusion current also in addition to drift current? When light is incident on a PN junction based solar cell from one side, would not we have a diffusion current also in addition to drift current?
Let's understand so you're thinking of a scenario like this. There's a depletion region, let's say this is N and then this is P. Okay. Now what you're saying is you are essentially having light incident on this side. And the question is, would not there be a diffusion current? Well, you could have a diffusion current. The question is, let's assume that nothing much happens. If you look at the generation rate, right? Generation rate is usually higher in the depletion. The generation rate is higher here in the depletion region. Why is that? Well, the semiconductor tries to come back to equilibrium, correct? So in the quasi-neutral region, so to speak, these regions, you don't have much of generation of electron hole pairs. So now, it depends on what kind of a absorption coefficient the semiconductor has. Okay, if you take a very thick region, for example, if you take a thin region, first let's start with the thin region. Okay, let's assume that this is the width of the depletion region. The depletion region width is small. Okay, how small? Let's assume a couple of microns. Okay, a few microns. That's actually quite large. In this case, okay, let's assume that this is an intrinsic. That's even better. Yeah, that will make it more relevant to what I'm talking. Okay, let's assume that the intrinsic region width is small, a few microns. Then most likely what will happen is your implies EHP generation is almost uniform. Okay, can be assumed to be uniform. Can be assumed to be uniform. Okay, and then now, yeah, first, when you have this field also, there's a certain current that flows like this, and then the center carriers will swept away both sides, right? The holes and the electrons will separate. Now, when you have a large W, and W is large, okay, let's assume tens of microns. In this case, there's going to be non-uniform generation. The reason is when you shine photons, they get absorbed, create electron hole pairs, and some of them will penetrate, create electron hole pairs, right? So there's an absorption coefficient associated with that, basically, which tells you that the intensity is going to be some I naught if I take it exponential minus alpha x, where alpha is my absorption coefficient. So because of which, you're going to have a gradient to start with itself. There's going to be a gradient in the electron hole pair distribution, right? There is this drop in the electron hole pair, because of which there can be some diffusion as well. Okay, so generally that's why it's very tricky to talk of only diffusion or drift. So we say we have a drift diffusion modeling. We call it drift diffusion model. Okay, so we use this. I mean, there will be a combination of drift and diffusion. It finally depends on the magnitudes of the fields we're talking about. Okay, it's not very easy to say that only drift exists or only diffusion exists. Well, I mean, in cases like a PN junction, we can say that, yeah, here it is mainly drift dominated, here it is diffusion dominated. But there's still going to be other part also. All right. I hope that answered your
Right,
question,
sir.
Sandeep.
Yes,
Right.
sir.
Yep. So finally, it depends on if you have a non-uniform concentration of electrons and holes, you're going to have a diffusion. You can't avoid it. Okay. In this first case, the
Okay.
absorption, the width was small. So more or less, the electron hole pair concentration is uniform. So I don't expect too much of diffusion in one way, right? Because equal number of holes are going, electrons are going, so nothing much happens. But if you have a large width, yes, there is going to be a decay in the electron or hole concentration. And because of it, there is going to be certain amount of diffusion.
So, but practically large width is desired, right?
In photodiodes, yeah, you get more absorption cross section, right? The issue is if
Yeah.
you have large widths, the response time. See, there are multiple things we have to optimize for. You want the carriers to move into the terminals as quickly as possible. Let's say you want to operate a photodiode in picosecond lifetime. Okay, but the carrier itself, there is certain velocity and there's a certain electric field, there's a certain mobility, so the velocity is going to be limited. So the speed of the diode is going to be limited. If you make it very large, there's going to be a lot more parasitic capacitances, and the speed of operation, even resistances, RC will be larger. So because of that, you will essentially have slower operation of the device. Okay? So if you want fast response times, you want to make the photodiode smaller. Okay. If you want to have large sensitivity, then you have to make it larger device. So there's a trade-off. You design how you want to. Okay. You can also play some interesting tricks on the design of the photodiodes.
Okay, sir. Okay.
Yeah. So what's the difference between gate overlap?
Capacitance.
What's the difference between gate overlap capacitance and gate source capacitance?
What is the gate source capacitance?
In diagrams, I have seen that it's drawn from the
You
gate
have me
terminal
at a
to the.
disadvantage. Okay, let's call it source and a drain. So overlap capacitance is reasonably simple, isn't it? Correct?
Pardon,
Do you have
sir?
any So this is my gate, right? So do you have an overlap capacitance in the way I have drawn it?
No, no.
No. Basically, usually what happens is you first define your gate area and then you define your source drain diffusions. So it happens that some of the gate is actually under the gate also you have the diffusion of the source and drain regions. Okay.
Yes.
So now because of this, there's an overlap between the source and the gate and the drain and the source and the gate. Sorry, gate and the drain
Yeah.
and GS and GD, right? There's an overlap
GD,
capacity.
yeah.
So these are basically overlap capacitances because of during the diffusion or the doping process, some amount of diffusion is unavoidable. Okay, we're going to have that. Now, other one you mentioned is gate source capacitance. Well,
Yes,
gate
sir.
source is effectively gate drain. Overlap capacitance only is what I can think of. Okay,
Okay, sir.
but
I got
you know,
confused. I thought that they both were
yeah.
different.
No, the question is, there's a bit of a challenge here. Okay, I'll tell you what. Now, you think of a scenario like this. How do you measure capacitance? Okay, how do you measure capacitance? If you have a two-terminal device, let's say, I'll have two-terminal devices, gate and source, right? This is my source and this is my drain, right? And there's also this thing called bulk. How do you measure capacitance? Well, the way we measure capacitance is, typically you say that you have this sort of it's not a linear capacitance, it's a non-linear capacitance. We agree to that? It's not a fixed capacitance. It will change as a function of voltage. So what you do is you have a DC bias, VDC, which goes like this. And on top of this, there is a small AC that writes. You essentially do basically dQ by dV. Okay. This is what you're trying to do. For measuring capacitance, you change the voltage, AC voltage, a small, for example, this could be just a 50 millivolt signal, 50 millivolts AC. Okay. Riding on a DC signal. You do the small change and then see how the response is. If there's a lag, you figure out how much it is, and based on that, you calculate the capacitance. Okay. Now the question is, if you have a device like this, and depending on the bias conditions, the capacitance can be very complex. Okay. For example, think of a MOSFET which is biased in inversion, a linear mode. Okay. There's a small charge that is, there's going to be this inversion charge that is sitting here, right? The MOS.
Yes, sir. Channel is formed.
Channel is formed now in the linear region. When channel is formed, okay, now I will bias it in such a way that I am essentially grounding this, and grounding this. Now, as I change voltage on the gate, where will the corresponding delta Q come from? Right?
So the electrons will compensate for the charges deposited
Yeah.
on gate.
Correct. Electrons will compensate in this case. Let's say it's an NMOS device. Electrons will compensate. You're right. The question is, where will they come from? If you somehow had, instead of this, let's say, hypothetically, I'll say that I have an LCR meter here. Okay. Let's assume that that's a kind of a meter that exists. That essentially, if you put it like this, and it will measure C, the capacitance. Now, this is slightly involved, Sandeep. You don't have to worry about it right now, but since you asked, I'm talking about this.
Okay.
Now, if you have a capacitance meter, you're changing something on the gate. Okay. But let's say the corresponding counter delta Q, right? Minus delta Q. Let's say you're introducing some plus delta Q here. The minus delta Q comes from this side and this side, both equally. Correct?
Yes, sir.
So,
Because increasing the gate voltage, I think, pushes down the energy band.
no, that is all, that is basically a different thing. That is about threshold and how the threshold lowers and current flows. That's okay. What I'm saying is, let's say okay, take a step back. Take a step back and look at what happens to a MOS cap in accumulation. Okay. If you have a device like this, let's say this is my 0 and this is my TOX, let's say, minus TOX. So if I want to bias this in accumulation, I'll have holes. So I'm going to have a hole charge like this. What to be my charge? My whole charge accumulation, right? These are all holes that are accumulating. Here, there's a minus electrons accumulating on the interface. Now, if I change the voltage slightly, what will happen is there's an additional plus delta Q and minus delta Q. This
Yes,
is
sir.
delta Q, and this is delta Q. And this is forming just across the gate oxide only. So the capacitance is going to be oxide capacitance, Cox, how much ever that is. Okay,
Okay.
that's what we are measuring. But now, when we bias it in let's say, we have inverted and we have a linear mode operation. So in that scenario, if you think of it, you have now plus charge here, and there's a minus charge on this side, isn't it? Okay,
Yes.
this is my Q and this is my minus Q. Now this minus Q, effectively it seems like half of it is coming from here, half of it is coming from here, right?
Okay.
So it's connected to both. There's no reason why only one side it should come. So if you measure the capacitance in the linear region across just the gate and the source, gate and the source or the gate and the drain, if I took it CGD or CGS, gate source capacitance, both will be Cox by 2. Okay?
Okay, because both are equally contributing charges.
Charges. So basically, you have to think of where the charges are coming from. And if you go to saturation, for reasons which I will not explain to you, okay,
Okay.
the CGD becomes 0 and CGS becomes 2 by 3 Cox.
Okay.
Okay. So essentially, the capacitance of this device becomes very complicated. Depending on the mode of operation, you can have Cox, you can have Cox by 2, you can have Cox into 2 by 3, and so on. Okay. Depending on the bias regimes. Now, the question is, how much is the relative contribution? Okay.
Okay.
Is the overlap capacitance large or this capacitance large? It all depends on the geometries and so on. Okay. Typically, yeah, that's all I can say. This is slightly more tricky to understand.
Yeah, but when we getting electrons to compensate for the gate voltage, even in the case of a MOS cap,
Sorry.
in the case of a MOS cap, when we were trying to invert,
Yeah.
when we getting enough electrons to compensate for the gate charge, positive charge.
Of course. There it's simpler because you don't have the source in the drain regions, right? They're only
Yeah,
coming
but
from here. But of course, there is a
so,
capacitance change, and then it's either HFCV or LFCV.
here
sorry,
also
it
we will
seems
be
like
getting some electrons from
one
the bulk,
second. I'm
right?
sorry, it seems maybe an urgent thing. Just 1 second, I'll take this. Somebody is calling me. Sorry, guys. Yeah. So you're
Yes,
yeah.
sir.
If you have a MOS cap, right? Of course, there's going to be some difference here because it's easier in some sense. You have the LFCV and HFCV, right? There's only gate and the bulk capacitor. There's nothing else. All right.
All right, sir.
Yep.
But in the case of MOS cap, from where did we get the electrons to compensate for the gate voltage? Was it from the
That's a
bulk?
very nice question. You should listen to that. I mean, you should listen to the lecture in detail. So essentially, what's happening is you have this is my oxide, right? Now, first you deplete. Okay. When you deplete, you have a depletion region underneath this schematically, right? Now, whenever you deplete a semiconductor, what happens? This is my oxide, right? This is my substrate, right? This is my metal on the top, correct?
Yes, sir.
Whenever you deplete a semiconductor, what happens? It tries to come back to equilibrium. How does it come back to equilibrium? Okay. You have generation of electron hole pairs. Okay.
Right, sir.
Whenever in PN junctions, for example, in this kind of a scenario, right? Wherever we are injecting carriers, right, by diffusion, let's say we're injecting holes here and electrons here. There's excess minority carriers. Whenever you have excess minority carriers, they recombine. Whenever you have depletion of depletion of all charges here, you have generation of electron hole pairs. When you have generation of electron hole pairs, if you look at the way the fields are in this structure, there is this oxide field. There is a electric field like this. Sorry. This is my X and this is my, let's say, electric field, the way the electric field is. And then there is this. This is my Tox, and this is 0. This is the edge of the depletion region. So you have a positive electric field in this case. So whenever you have electric field, so electric field is going into the substrate like this. So whatever electron hole pairs are generated here, the holes will go here, the electrons will come to the interface. And this generation is a source of the inversion charges. Okay?
Okay.
Yeah. So that's how you have the inversion charge epinectin. All right? And that's why it takes time. And you also need to have a certain width of depletion region before you can generate sufficient electron hole pairs and sufficient inversion charges. Yeah. So please explain the steady state minority carrier concentration diagram for solar cell.
Yes, in the case of a solar cell, my doubt was that when we shine a burst of photons at the depletion region, electrons and hole pairs are generated, and they migrate to the opposite sides because of the barrier potential, barrier
electric field. Yeah.
Yeah, the holes migrate to the p side, electrons migrate to the n side. But aren't they majority carriers there? Then why do we mention that the minority carrier concentration changes? And in the graph which was drawn, it was shown that the minority carrier concentration is to be added to the equilibrium
Okay,
constant.
I'm sorry. This is in week 11 or 12. I forgot actually. It's been a long time since I saw this.
It's in week 11, sir.
Week 11. So, what did I draw? Where? These are absorption coefficients. No, essentially what's happening is you are generating this and you have this field which is driving the holes out, essentially, right?
Yes, sir.
Now, what are we saying? We're not injecting any excess minority carriers, by the way, correct?
Yeah, correct.
We are not injecting because of external bias, nothing. It's just without a bias, you're giving this, you're putting a resistor. Now we generate this. So where will the holes go? If they come here, if a hole comes into this point, it has to drive the hole out here, no? Correct?
Yes, yes.
Similarly, electron comes here, electron has to flow in the external circuit. That's how you have the circuit forming consisting of both electron and the hole currents.
Right. But when we move to the carrier concentration graph,
this one.
Yeah, this one.
Okay. Yeah. Good.
There we have mentioned that delta ends up P.
Yep.
That's
Correct.
the excess minority carrier concentration in the P side, right?
Well, the question here is, in the P side, you have generated some excess charges. You're shining the electric field everywhere. And because of that, there is some excess minority carrier concentration created. Okay, uniformly.
But how would it be minority carriers? Because when we have in the depletion region, when we have holes formed, they move to the P side. They are the majority there.
No.
That's where I got confused.
This is not moving from the N side into the P side. Okay.
Yeah, from the depletion region, they are moving to P side.
Well, no. You don't have to do that as well. So now you shine electron hole pairs. Now, sorry, when you shine light, let's say in this semiconductor, right? This is actually a small problem here. Okay, when you shine light, what happens? On the semiconductor,
in the depletion region, we have electron hole pairs being formed.
Not only that, let's assume this. Take this case. We have taken a case, right? You have taken an ND. Let's say you dope it only with the N-type semiconductor. Let's say ND is 10 power 15. Okay. Now, if you shine this, N equal to 10 power 15, P equal to 10 power 5, correct? Initially, yes. Equilibrium. Now, when you shine light, so much of light, let's say there is some generation rate, okay? G, some generation rate, G. And you saw that basically G tau is going to be equal to your excess minority carriers. Okay. So in this case, essentially, we are talking about a situation here, right? Where this part. It's an N-type semiconductor we are talking. So you're going to have excess, both majority and minority carriers. G tau is going to be the rate. So G tau is going to be some rate. And so because of that, you're going to have delta N equal to delta P equal to G tau, correct?
Correct.
So when you have generation, now because of this, your carrier concentration of this increases by delta N, this by delta P. Now, the delta P is very, very significant compared to the original P naught. Okay? P and naught, and this is delta P, right? This is much larger. See, comparable.
In the case of the PN junction, that delta P will not move to the N side, right?
No, this delta P is only everywhere, it's uniformly being created, right? Depending on the doping, we have delta N here and delta P here. But this, by the way, this generation rate is going to be quite small actually. Okay. Now, what happens is you have minority carriers, holes here. The electric field is in this case, which way? In this it's N and P, right? So electric field is in this direction.
Into P.
Into P. So electrons will move this side and holes will move this side.
Yes, sir.
So this excess electrons will try to move this side. But it only happens within a couple of diffusion lengths. Beyond that, there won't be any change.
Okay.
Right? It is not that these holes are getting injected into this. Well,
yes, sir.
Yeah, I mean, because of the field, whatever is close to the interface will get swept away. Okay.
But in the expression for the delta NP, how did we have GL times tau P naught? Shouldn't it be tau N? Tau N naught.
It should be tau and naught. But in this case, this side you see here, this is excess. I think this is a mistake in this because this is N, this is tau N. This should be P, right? This is not delta NP. This is PN, right? This should be.
Yes, sir. P.
There's a mistake here, right? There should be delta PN. In the N region, the holes, excess holes, right? This is also, yeah, that's what I think I mentioned here. Essentially, this is PN and delta PN. They have written it as NP, which is not the case. Oh, I'm sorry. I think, I'm sorry, Sandeep. Actually, I forgot there is another course that I have to take a session. Okay. 7:35. Okay. Sandeep, can you just send me an email? We can try to schedule a one-to-one session.
Okay, sir.
Yeah, I'm sorry because I have to encrypt. Sorry for Ritu, you have to speak up, otherwise I won't even see all these things. Okay. I have another course that I have to attend to. Okay. I'm sorry, Sandeep. We'll just send me an email, Naresh D, and we will schedule a session.
I'll mail
Alright?
you.
Yeah.
Thank you, sir.
சுண்டல் ஒயிட் சுண்டல் போட்டிருந்தேன் அது சுண்டல் பேக்கெட் வாங்கிட்டு போய் கொடுத்தேன் செஞ்சு எடுத்துட்டு போய் கொடுக்கணுமா
கருப்பு கொண்டாங்கல தான் நம்ம இருக்கு
ஒயிட் சுண்டல் நான் அது போடல நான் இதுதான் போட்டிருக்கேன்
யாரு ஒயிட் சுண்டல் போடுறா யாரு ஒயிட் சுண்டல்
தெரியல சந்தன பெலா அண்ட் வெசல் குங்கும் சந்தன பெலா
பத்திரமா திருப்பி கொண்டு வரணும்
அதெல்லாம் எங்க டிபார்ட்மெண்ட்ல தான்
ஒரு ட்ரே சந்தன பெலா
ட்ரே எல்லாம் தேவையில்ல
அதை எதுல வச்சுப்பீங்க பூவெல்லாம் இந்த பட்டர் ரோஸ்லாம் வாங்க சொல்லியிருந்தேன் 5 ரூபாய்ல